Hello everyone, welcome to this lecture. So, just to recall, in the last lecture we had seen the Merkle-Damgard paradigm for constructing collision resistant hash functions for any size inputs, and in this lecture we will see the stage 1 of the Merkle-Damgard paradigm, namely how to construct the fixed length compression functions. So, just to recall, pictorially this is how a Merkle-Damgard paradigm will take any fixed length compression function little h, which is collision resistant, and apply it iteratively to obtain or a hash function which can hash inputs of any size. So, now the interesting question is how exactly you obtain this fixed length collision resistant compression function little h at the first place. So, pictorially this function little h takes an input of size L plus n bits, which can be passed as 2 inputs, an input m of L little l bits and another input t of little n bits, and together it will compress it and gives you an output of size little n bits, right. So, that is how you can interpret this fixed length compression function, and it turns out that there are two approaches to construct this function h. The first approach is to construct design constructions based on number theoretic hard problem or number theoretic assumptions. So, when we will start our discussion on number theory and public key cryptography, we will come back and we will see how to use some number theoretic hardness assumptions to construct this function little h. And this approach is not used practically, because even though the constructions, their running time, they are polynomial in the security parameter, the actual running time when deployed in practice is of order of several magnitudes, and that is why we do not use the instantiations of this function little h based on number theoretic hardness assumptions. Instead, what we do is we design constructions, we go for constructions based on block ciphers, or we can take any of the existing block ciphers, say AES, DES, or we can design dedicated block ciphers, and these are the constructions, or these are the instantiations of the function little h which we use in practice. However, interestingly, the security proof of the constructions based on these block ciphers, they are in very unconventional model. In the they are unconventional model in the sense we make very strong assumptions from the underlying model and then give the security proof. So, let us see this approach of how to construct collision resistant compression function, fixed length compression function from block ciphers, and there are several constructions available. We will see one of the construction which is called as Davis-Meyer construction. So, what you are given is a block cipher which you can interpret as a keyed pseudo random permutation, taking a key from the key space and input x from the block space and giving you an output, where the output and the block size are the same, namely both of them belong to the set this fancy x. And using this, we design a compression function little h, which I denote as h sub dm, namely we can call it as Davis-Meyer compression function, which takes an input right of size this cardinality of k and cardinality of x space. So, namely it takes two inputs, one input is interpreted as m and the other input is interpreted as t, and the output of this compression function is defined as follows. We evaluate the block cipher with respect to the key little m and treating the t part as the block, and the output is again XORed with the t part of the input of this Davis-Meyer hash compression function. So, that is how this Davis-Meyer compression function is evaluated, right. So, the interesting part here is that the message block in the hash chain. So, remember that this function little h is going to be plugged in the hash chain of the Merkle-Damgard paradigm, right, when we are evaluating the overall hash function big H, right. So, that is why the pictorially I am representing this function little h consisting of two inputs. One input will be the block part of the message which we want to hash in the bigger message, and one will be the t part which will be coming from the outcome of the previous invocation of the little h function, right. And the way we are designing this Davis-Meyer compression function is basically the message block on which we are going to operate this Davis-Meyer construction will be treated as the key for the pseudo random permutation of the block cipher, and it need not be uniformly random, right, because attacker could have full control over the bigger message which it want to hash as per the Merkle-Damgard paradigm, and that means it gives the attacker full control over what exactly is serving as the key for the block cipher when the block cipher is internally used in the design of the Davis-Meyer compression function. However, even though the adversary has the full control over the key which is used in the underlying instantiation of block cipher in this Davis-Meyer compression function, it can be proved that the overall construction of this Davis-Meyer compression function is indeed collision resistant under special conditions, right. That means there is nothing to worry about here, even though you might be wondering that or we have discussed that block ciphers remain secure only if the key is not known to the attacker and the key is uniformly random. But the way we are operating or using the block cipher in this Davis-Meyer compression function is that the message block which we are one part of the message block, that the block of the message which we are going to use or apply the hash function little h, right, it is fully under the control of the adversary, and that is actually serving as the key for your blocks underlying instantiation of your block cipher, and that need not be random, but still we can prove that under special conditions the way this output of the Davis-Meyer construction is defined, overall the function the Davis-Meyer construction that we have constructed here is indeed collision resistant, right. So, here is how we have constructed the Davis-Meyer compression function, and as I am continuously saying that we can prove the collision resistance of the Davis-Meyer construction under special assumptions. This is because we do not know how to prove the collision resistance of the Davis-Meyer construction that we have given, just assuming that the underlying block cipher is a strong pseudo random permutation. It is not sufficient to just assume that the underlying function f is a strong pseudo random permutation and give a proof that the Davis-Meyer construction is indeed collision resistant. However, interestingly the proof of the collision resistance of the Davis-Meyer construction is known in the ideal cipher model, which is kind of a hypothetical setting because it makes very strong assumptions about your underlying block cipher. So, let us see what exactly is this ideal cipher model. So, in ideal cipher model, the underlying block cipher or the keyed permutation f is abstracted as a collection of several truly random permutations where each member of this family or each member of this collection is indexed by the underlying key with which we are going to operate the function f. So, remember the block cipher, it takes a block input and a key input. So, what basically we are assuming in this ideal cipher model is that even though we are given a single even though we are given the description of a single f function, as soon as we fix a value of k, that gives a instantiation of the f function which can be treated as one member of a bigger family. So, different values of the k which are used in the instantiation of your function f will give you different members of the bigger family, and that is why we are now viewing that even though we are given we are given the description of a single f function, when used with different k it gives you different members from a bigger family, and that is what we mean by function f abstracted as a collection of truly random permutations. The second property in this ideal cipher model is that once we know a family member f k1 and another family member f k2, namely these are the instantiations of your block cipher with the key k1 and the key k2. The assumption here is that the family member f k1 and the family member f k2, namely the keyed permutations f k1 and f k2, they are independent of each other even if the keys k1 and k2 are dependent or related to each other. That means even if it so happens that k1 is almost the same as k2 except say the last bit, the assumption in this ideal cipher model is that the function f k1 will be completely independent, in the sense its output will be uniformly random and it will be completely independent from the outputs of the function f k2, right. So, that is a second property in this ideal cipher model. So, till now there is nothing unconventional here that we are assuming about the function f, because when we are assuming that function f is a strong pseudo random permutation, that means even though it is not a truly random permutation, it gives you pseudo randomness guarantee. That means we can assume that it behaves like a pseudo random permutation, but in the ideal cipher model, we are making slightly more stronger assumptions. We are assuming that each member of this bigger family is indeed a truly random permutation and independent of each other. The strongest property, or the you can call it as the most unconventional property in this ideal cipher model, is that no party or no entity in the system who is going to use a cryptographic primitive which makes use this block cipher will have access to the code of the function f and the code of the function f inverse. That means, if at all any entity wants to compute the value of the function f with respect to some key, it will make oracle access, or it will make oracle calls to the keyed permutation fk, and it will just get back the value of the keyed permutation on the input for which it wants the value of the fk. In the same way, if some entity wants to know the value of f inverse with respect to some input key k and some input y, then it can make just oracle call to the f inverse oracle, and it will get back the corresponding output, but it will not get any access to the code of the block cipher. So, that is the most unconventional assumption that we are making in the ideal cipher model, because in reality when we are designing the Davis-Meyer construction and instantiating it, we need the actual block cipher which we are going to plug in this construction of the Davis-Meyer construction, and every entity who is going to use that instantiation of the Davis-Meyer construction will know the code of the function f, including the adversary. But when we are analyzing the security of the Davis-Meyer construction, the assumption that we are making in the ideal cipher model is that no one will be knowing the code of the function f. It is just a collection of several random members. If you want to talk to one random member, just make an oracle call, right. So, assume now we are in the ideal cipher model. What we are going to prove is that this Davis-Meyer construction of fixed length compression function that we have given here indeed is a collision resistant function. So, remember that indeed it is a compression function, because we are taking an input of size n plus l bits and giving you an output of size l bits. So, it is a compression function. What we have to prove is that in polynomial amount of time, it is difficult for an adversary to come up with a pair m comma t and m star comma t star such that the output of the Davis-Meyer function is the same, where the Davis-Meyer construction is using a block cipher, right. So, since we are going to analyze the security of this compression function in the ideal cipher model, any adversary who would like to find out collision for this Davis-Meyer construction, it needs to evaluate the Davis-Meyer function on several messages of its choice, right. Then only it could come up with a collision. And to evaluate the Davis-Meyer function on messages of its choice, internally it needs to evaluate the function f and f inverse as well, because we do not know what exactly is the strategy of the adversary. It may evaluate the underlying f on several message several m comma t pairs. It could evaluate the underlying f inverse also on several messages of its choice or several inputs of its choice, and then only it could come up with a corresponding collision. But since we are now in the ideal cipher model, what we are going to assume is that even the adversary who would like to evaluate the underlying f and f inverse on inputs of his choice to come up with a collision for this Davis-Meyer function will make oracle queries, right. It will not be, because it will not be knowing the code of the function f and the code of the function f inverse. So, that is why to make this oracle queries, to incorporate these oracle queries from the adversary to find out the collision, these oracle queries are incorporated in the hash collision experiment when we analyze the security of this Davis-Meyer construction in the ideal cipher model. So, remember, in the actual hash collision experiment in the non-ideal cipher model or in the standard model, adversary can query anything. Adversary need not have to query anything, because it will be having access to the code of the function f or f inverse if we are using any f or f inverse in the design of the underlying hash function. But now, since we are in the ideal cipher model, even adversaries interaction with the function f and f inverse will be through oracle queries, and that is why they also need to be incorporated in the modified hash collision experiment. So, the modified hash collision collision experiment is as follows. So, we now assume that both the experiment as well as the adversary will have oracle access to the family of the functions fk and the family of the functions fk inverse. So, you can imagine that these oracles fk and fk inverse are kind of lying in the sky, where no one can see what exactly is the code of the function fk and fk inverse, and if anyone wants to make a compute the value of the function fk for k of its choice, it just shouts to the sky that please sky give me the value of this function fk on this input, and it will see the value of fk on that input, and same way the interaction with fk inverse is handled here, right. So, that is why I am putting this family of functions fk and fk inverse inside a box here. No one can see what exactly is happening inside the box. Everyone is all the interactions are going to be just an interface. You supply some input and you get back the output. So, the modified hash collision experiment is as follows. So, remember the goal of this adversary is it knows the description of your Davis-Meyer hash function, namely it knows that the Davis-Meyer hash function is basically f of t under the key k under the key m XORed with the t part, right. So, and the goal of the adversary is basically to come up with a pair m comma t and m star comma t star, which constitutes a collision with respect to this Davis-Meyer function. But since we are in the ideal cipher model, any value of f which adversary would like to compute, or any value of f inverse which the adversary would like to compute, will be now made through oracle queries. So, imagine if adversary would like to know the value of f with respect to this key ki and on the input xi. So, it can make an oracle query, and what the oracle is going to return back is it is going to return back the value of the function f with respect to the key ki on the input xi. And if the adversary sees this response, then basically what adversary sees is the value of the Davis-Meyer function on the input pair ki comma xi, because the value of the Davis-Meyer function on this combined input ki comma xi will be the value of the function or the block cipher f on the input xi with the key ki XORed with the input xi. But since the adversary is in the ideal cipher model, he cannot compute the value of f of xi with the key ki. That is why it has made an oracle query here. So, that is how the adversary is going to compute the value of Davis-Meyer functions on messages of its choice. It turns out that this is not the only way by which the adversary could compute the value of the Davis-Meyer function on inputs of his choice. It could take the help of the inverse oracle access as well. Say for instance, it can ask, hey inverse oracle, give me the value of the inverse of the function under the key ki on the input yi, and in response what the oracle is going to do is it is going to return back the inverse of this function on the input yi under the key k. Under the key ki. Sorry for the typo here, it should be under the key ki. Right. And once the adversary learns the inverse of this yi under the key ki, that gives him the value of the Davis-Meyer function on the input ki comma xi, because the way Davis-Meyer function is constructed, the output of the Davis-Meyer function on this input ki comma xi would be like this. So, by making oracle queries to the fk family and by making oracle queries to the fk inverse family, we can assume that the adversary is now going to compute the output of the Davis-Meyer function on several messages of its choice, namely polynomial number of messages, because our adversary is polynomially bounded. And now finally he submits a collision, namely a pair of inputs m comma t and a pair of input m star comma t star. And the security definition here is that we will say that this collision resistant experiment is successful for the adversary in the ideal cipher model if in this model where adversary is now making or given oracle access to the fk family and fk inverse family, the probability that the adversary could come up with a collision is upper bounded by a negligible function, and the collision is now specific because now we are analyzing the collision with respect to the Davis-Meyer construction. So, the output of the Davis-Meyer construction for the m comma t message which the adversary is submitted will be this, and the output of the Davis-Meyer function for the message m star comma t star that the adversary has submitted will be this. Our goal is to analyze what is the success probability or what is the probability that this condition hold. The security definition is, we will say that the Davis-Meyer construction is collision resistant in the ideal cipher model if the probability that any polytime adversary could come up with a special m comma t and m star comma t star satisfying this condition is upper bounded by some negligible function. And what we are going to prove is that indeed the Davis-Meyer construction that we have given constitutes a collision resistant function in the ideal cipher model, provided the size of the X domain or the X set is sufficiently large. More specifically, what we are going to prove here is that any polytime adversary or any adversary A issuing q number of ideal queries together all together to the F family and F inverse family can find a collision with probability upper bounded by q times q plus 1 over the size of the X set. Right. So, here q is the total number of queries which the adversary is allowed to make to the F family and the F inverse family. Right. So, it is not q for the F and q for F inverse all together. Right. So, if it is making S number of queries to F and T number of queries to F inverse, then S plus T is basically q. And what we are going to prove is that in the ideal cipher model, any polytime adversary making q number of queries, his success probability of finding a collision in the Davis-Meyer function is upper bounded by this quantity. So, what we are going to do here is we consider the query numbers I comma j, where I is less than j. That means, assume that adversary has already queried up to j minus 1 queries altogether to the combined F and F inverse family, and now he is making the jth query. And any time when he is making the query, the combined the response from the query gives him the value of the Davis-Meyer function on some input pair, right, because that is we had already seen that in the last slide. So, if he is making queries to the F family, then based on the response it gets the value of the Davis-Meyer function on some input, and if he is making a query to the F inverse family, then again based on the response it gives him the value of some input, gives him the value of the Davis-Meyer function on some input. So, what we denote here is that the ith query based on the response, whatever hash value he learns, I denote it as h sub I, and based on the response that he has based on the response for his jth query, whatever hash value that he learns for the Davis-Meyer function, I denote it as h of j. And now I am interested to compute what is the probability that the ith hash value and the jth hash value which the adversary learns in this ideal cipher model are the same. So, now there could be two cases here. Assume that the jth query which the adversary is making is for the F family. So, when he is making a jth query to the F family, then he can make a query of this form. That means, basically he is asking for the value of the family member F of kj on the input xj. So, he will see the response which I denote as yj, and based on the response he basically learns the value of the Davis-Meyer function on some input. Basically he learns the value of the Davis-Meyer function on the input kj comma xj, and that is denoted by as h of j, and this will h of j will be this value, right. So, we are interested to analyze what is the probability that the jth hash value which the adversary has learned by making this query to the Fk family is the same as the ith hash value which the adversary has already learned while making the ith query. And remember, the ith query could be either to the Fk family or to the Fk inverse family. So, the probability that the ith hash value which the adversary has learned is the same as the jth hash value which the adversary has just now learned are same. It is the same as the probability that the family member Fk of j when evaluated at the input xj gives you this output. If that is the case, then h of I and h of j will be the same. But since we are in the ideal cipher model, right, what is the value of the family member Fkj on the input xj? Well, it is a uniformly random value independent of each other, right. It is a uniformly random value over the x set, and it is different from all the previous Fkj values for which the adversary might have already asked the output value, right. So, remember, we are in the case where I is less than j, we are analyzing the probability with respect to the collision for the output of the ith query and the jth query. So, in the worst case, it may so happen that for all the previous j minus 1 queries, the adversary might have asked for the value of the function family with respect to the key kj, and in response the adversary might have seen the output of the family member Fkj for various inputs. And since Fkj is a permutation, right, when the oracle is giving him back the response for the Fkj family on the jth input, that has to be different from all the previous j minus 1 outputs that he here that the oracle has already returned to the adversary. So, the probability with which this condition, namely the output of the jth query under the key fkj is equal to this, is always upper bounded by 1 over the size of the x set minus j plus 1, right. So, that is a probability with which by making the jth query to the fk function, the adversary can hope that it gets a collision with respect to the output of the ith query which he had made in the previous interaction with the oracle. On the other hand, it may so happen that the adversary's jth query is for the f inverse function, right. So, it could ask for the value of the inverse, it could ask for the oracle service for this input for the f in from the f inverse oracle, and in response it gets back the output. Basically, it sees the inverse of the input yj under the key fkj, right. So, he is basically asking for the access to the f inverse kj member on the input yj, and it gets back the output xj, and based on that it learns the jth hash value, right, on this message, namely the value of the Davis-Meyer function, and that the output h of j will be this. Now, in this case, what is the probability that the jth value which the adversary has learnt here is the same as the output of the ith query which the adversary has already learnt in the previous interaction. Well, the probability of that is the same as that the probability that your f inverse function under the key kj on the input yj gives you an output which is same as the XOR of hi and yj. And again we can run the same argument that we have done for the case on your left hand side, right. Remember that in the ideal cipher model, each of the family members fk and fk inverse, they are truly random and independent of each other. So, that means this family member f inverse kj is like a truly random permutation, and it may so happen that all the previous j minus 1 queries the adversary could have made with respect to the family member kj. That means, in the worst case it might have asked for the inverse of this family member, he might have asked for the value of f inverse kj on various y values of his choice for all the j minus 1 queries. So, now when for the jth query, when the oracle is giving him back the response is going to be different from all the previous responses that the oracle has given with respect to the j minus 1 queries. So, that is why we can now safely conclude that the probability that hi is equal to hj happens where hj is now defined like this by making a by adversary making an oracle call for the inverse function is upper bounded by 1 over the size of x set minus j plus 1, right. So, in both the cases, that means irrespective of whether the jth query is for the fk function or the jth query is for the fk inverse function, the probability that the hash value which adversary learns due to this jth query matches the output of the ith query is upper bounded by 1 over the size of x minus j plus 1, right. So, that is a fact we have established now. And how many queries adversary is actually making here? We are making an assumption that adversary is making total q number of queries total, right. So, and what we have analyzed is that out of those q queries, what is the probability that a pair of distinct queries gives him a collision for the Davis-Meyer construction in the ideal cipher model. That probability we have calculated just now. So, now what we have to do is we have to apply the union bound, namely we have to take this probability and sum it up over all pairs of distinct I comma j, where I and j ranges from 1 to q. So, let collision be the event that by making q number of queries to the function to the family f and f inverse, adversary obtains at least one pair of collision. That means, adversary obtains at least one I comma j pair where the hi value and hj value are same. So, it turns out that by applying the union bound, the probability of collision can be easily upper bounded by this, namely summation of j equal to 1 to q and internally summation I equal to j minus 1, the probability that the ith output and the jth output are same. And what I can do is that I can substitute the inner summation, because now I know that the value of each of the probabilities that is present in the internal summation is upper bounded by 1 over x minus j plus 1, and since I ranges from j minus 1, I can and there are j minus 1 such terms. So, in the numerator we get j minus 1 and each of those probabilities is 1 over x minus j plus 1. So, that is what we obtain, and if we further simplify then we can replace this inequality by this, namely what we have done here is I can always replace each of this minus j plus 1 by minus q, because j is always upper bounded by q, and if I take out this summation finally, since j ranges from 1 to q, I can replace an inequality by the inequality on your by this inequality. So, now let us analyze this final inequality for two cases. If the number of queries which the adversary has made in this ideal cipher model is upper bounded by the size of x over 2, then we can do some simplification here and end up showing that the probability of collision is indeed upper bounded by q times q plus 1 over the size of x set. On the other hand, if the number of queries which the adversary has made is greater than the size of x over 2, then trivially it so holds that probability of collision is upper bounded by this. That means it does not matter whether we are in case 1 or in case 2, in both the cases the probability of collision by making q queries is upper bounded by q over q plus 1 over the size of x, and that establishes the fact that we have stated in this theorem. That means if q is say some polynomial function in the security parameter, and if x is say some significantly large quantity, say some exponentially large quantity in the security parameter, then overall this probability turns out to be a negligible function in the security parameter. And that is why we can now safely conclude that the Davis-Meyer construction is secure in the or its collision resistant in the ideal cipher model, and adversary by evaluating the Davis-Meyer function for q number of messages in the ideal cipher model could not come up with a collision except with a negligible success probability, right. So, that brings me to the end of this lecture. Just to summarize, in this lecture we had discussed how to construct the fixed length compression function, and there are two approaches for that. One approach where we actually use number theoretic hardness assumptions and we get provably secure guarantees in the standard model, but we do not opt for those constructions as practice because the amount of computations which are involved in those constructions are of order of several magnitude. Rather we use constructions based on dedicated block ciphers or the existing block ciphers, and we had seen one of those construction, namely the Davis-Meyer construction, which is very simple, but it turns out that even though practically no attacks have been reported on that construction, we cannot prove the security of that construction just assuming that your block cipher is a secure block cipher or a strong pseudo random permutation. We have to make very strong assumptions in our model, namely we have to assume that we are in the ideal cipher model where block cipher is basically acting as a collection of or is a family of several truly random permutation, where the access to the block cipher is through oracle calls even for the adversary. Only if we make this ideal cipher assumption model we can prove the security of the Davis-Meyer construction. Thank you.